Hello, everybody, and welcome to today's webinar presentation, Accelerating Spark with Kubernetes, brought to you by Alluxio. Before we get started, I do have a few housekeeping items that I need to go over. First off, I want to make sure you all can hear me okay, so if you would, please post a message in the chat panel to let me know. Great. If you have any questions for our presenters today, please post those into the questions panel so we can get to them after the presentation. And if you experience any technical difficulties today, please post a message in the chat panel to me, the host, and I will work with you to resolve those issues. And last on my housekeeping list, we are recording today's presentation, and it will be made available shortly after today's event concludes. And now that we're through the housekeeping items, I would like to introduce you to our presenters. Our first presenter is Adit Madan. Adit is a core engineer at Alluxio. His experience is in distributed systems, storage systems, and large-scale data analytics. And he holds a BS from IIT. And now I'd like to do a quick sound check for Adit. So if you would say hello, Adit, audience, let me know if you can hear him by posting a message in the chat panel.
Hello, everyone.
Great. Looks like everyone can hear you. Our next presenter is Dipti Borkar. Dipti is the VP of Product and Marketing at Alluxio with over 15 years experience in data and database technology across relational and non-relational. Prior to Alluxio, Dipti was VP of Product Marketing at Kinetica and Couchbase. Dipti holds a MS in Computer Science from the UC San Diego. And now I'd like to do a quick sound check for Dipti. So Dipti, if you would say hello, and the audience, let me know if you can hear Dipti by posting a message in the chat panel.
Hello, everyone. Thanks for joining today.
Great. Looks like everyone can hear you all. So with that, I'm going to turn things over to you guys to begin the presentation.
Perfect. Thank you so much. And thanks for joining, folks. Today, we will be taking you through a few different topics about Spark, about Kubernetes, about Alluxio, and how, at the end of the day, all of these fit together. We'll end with a live demo if the demo gods permit. To begin, what we'll do is a quick overview of Alluxio to kind of help understand where it fits into the data ecosystem. We'll follow that up with an introduction to Kubernetes, understand the core concepts like pods, hosts, Helm charts, operators, and more. And then we'll talk about the deployment options for any stack. So as an example, we'll use the Spark plus Alluxio stack, and we look at the deployment options. And then finally, we'll conclude with a live demo. So let's get right in. So Alluxio, the journey actually began at the Berkeley AMP Lab. Our founder, Hao Yuan, was a PhD student and was working as a core contributor to Spark. The other projects that came out of at the AMP Lab were Spark as well as Mesos, and he was trying to address the data aspect of the distributed systems challenge. The original premise was around constantly changing storage systems over time, and the constantly evolving computes on top of it, and how we could simplify this with a new abstraction layer and orchestration layer that sits between compute and storage. And since then, we've come a long way. We have great backing from Andreessen Horowitz and won a few awards along the way. In terms of Alluxio, the project, we are an open source project. We have several contributors, 1,000+ contributors, and we'd love for you to take a look and contribute into the project. It's Apache 2.0 licensed, and so we have a community edition based on our open source as well as an enterprise edition. And we would love you to join the community. We have a Slack channel, and you can see our GitHub links. So it will be great to see some of you in there. Let's take a look at how the data ecosystem has evolved. If you think back 10 to 15 years ago, it started off with a simple, very simple stack. It was MapReduce, and then there was HDFS. There was one compute which was MapReduce, which did allowed you to perform a lot of batch jobs. And then there was HDFS. And Kubernetes at that point didn't really exist. All of this was either physical hardware or virtualized using, VMware and others. Containers weren't really a part of this big data ecosystem. But over time, this ecosystem has exploded. And every few months, there's a new framework, there's a new model, there's a new Python-based framework that's coming out. Some of the most popular ones right now are Spark, Presto, TensorFlow, and others. Hive continues to be used. And below this, you have a range of storage systems. Some of the data might be in on-premises HDFS, some of it might be in S3 or in another cloud. And this explosion has caused a lot of complexity in how the data itself can be brought to the compute. Unlike the MapReduce and Hadoop example that we see here, where it was a co-located stack nicely coupled, now we're in a separated environment where compute and storage are separated out, and they may be containerized, and they might need to be orchestrated by Kubernetes. And so there's a lot of complexity in how the data itself and the working set that's needed for these computes is brought into the compute and brought closer to the compute to achieve data locality. This could be with or without Kubernetes. But given this, that's kind of where Alluxio comes in. Alluxio helps with the separation of storage and compute and allows you to, in the simplest use case, cache data for Spark or Presto, or enable hybrid cloud environments or object storage. So let's take a look at a journey in terms of how users are moving from a very tightly co-located environment with Hive and HDFS to a separated environment and increasingly using containers and Kubernetes. So step one, everything is co-located. You have your MapReduce or Hive workloads on top of your HDFS. Everything is running on the same node, and you could have a 1,000 node or 2,000 node or n node cluster, but it is all co-located. But when you start disaggregating the storage and compute for flexibility reasons, to leverage the cloud, many other reasons, to offload CPU usage, users are now starting to look at separate clusters, a separate compute cluster and a separate storage cluster. And this allows for more flexibility. So compute can scale out independently on the CPU or core dimension, and HDFS or storage can scale out independently on the IO and amount of data dimensions. And from there, what we're seeing is more and more users are looking at bursting the data that is in HDFS into the cloud to get even more flexibility and to use compute on demand. And so if you have a Spark job, you want that's running an ETL job, you might want to bring up a cluster for a couple of hours, run the job, and then you're done. And so they're looking at ways to move data from the on-premises environment to the cloud to enable to do this. In addition to that, given the number of frameworks that are coming out, data engineers and data scientists are looking at new frameworks that can help them bring more insights from this data. And so that's another dimension that we're seeing, where to be able to support all these new applications and new frameworks, you need a data layer that can bring this data from various data silos into the compute environment on demand. And finally, you might want to move to object storage, either in the cloud or in premises. And these object stores are not inherently developed for analytical workloads. And so technologies like Alluxio speed this up by adding a caching layer, not only for data, but also for metadata to speed up the metadata operations. So this is a journey that many of you might be going through, and you might be in different phases of this journey. And for the cloud aspects of it, the cloud environments, we're increasingly seeing the container usage and Kubernetes being deployed, particularly on the public clouds. Each mega cloud has their own service. It could be GKE in Google, Amazon has their own, and Azure has its own as well. So Alluxio is a layer that sits in the middle, just like Kubernetes orchestrates containers for compute. Alluxio orchestrates data and the working sets for all these different workloads and brings that data closer to the frameworks. And there's different APIs that you can use to access data out of Alluxio. The most popular ones tend to be the HDFS interface, the Java interface, and on the machine learning, the Python framework side, we're seeing more usage of POSIX as well. And on the back end, if you will, what we call the southbound side, you have many different storage systems. It could be they could be S3 compatible, HDFS compatible, or NFS compatible. And because of all these different storage systems that you can access through Alluxio, when used along with Kubernetes, it allows you to run your data workload no matter where your data is stored, and it allows you to pull that data into your Kubernetes environments. So as I was mentioning earlier, there are a few key innovations that Alluxio brings because it's bringing your data closer to your compute. You have tighter data locality, which is lost in a separated environment when compute and storage are separated. And so it brings back data locality on a node level. And we'll take a look at the architecture in just a minute to see how it would exactly work. As I showed earlier, there's many different APIs that you could use. And so no matter what the file format is, let's say you have an ORC or a Parquet file or an image file, there are many ways of accessing the same data, the same file, based on the framework that you're using and the API that you're using on the top. And then the third innovation is the global namespace. And so from an application perspective, if you interface with Alluxio, it doesn't really know where this data is coming from. And so you not only achieve storage agnostic behavior, it's storage agnostic, it's cloud agnostic, as well as compute agnostic. So in terms of interfacing, in terms of actually writing code, reading and writing out of Alluxio, there's a few different ways to do this. You can see here that if you want to bring in a file and create an RDD, it simply, would be a simple Spark syntax that looks like this. You read the text file from the path. And typically, if these paths are HDFS or S3, all you need to do is, there's no real application code change needed. You basically just change the prefix to Alluxio and drop the class, update the class path, and so on, and you can access data from Alluxio just like you would from the other storage systems underneath. And there's a few other ways of in accessing and interacting with data stored within Alluxio. So here's a high-level architecture of Alluxio. It's a master worker kind of architecture. And you see a couple of different clusters here. You see a Presto cluster as well as a Spark cluster. The Presto cluster allows you to, within this cluster, let's say you have 50 Presto nodes, you will have 50 Alluxio nodes workers, which are co-located with those nodes in the same instance and in the same container. And we'll talk a little bit about how this works in the containerized environments in just a bit. And then the master is responsible for managing the metadata. It's a percentage of the metadata. It's not all the metadata because data gets pulled in from the underlying systems on an as-needed basis. So the metadata stored within the Alluxio master might be 5 or 10% of the entire data set that you might be using across your storage systems. We also have HA capabilities with standby masters and with either Zookeeper or using the Raft protocol. Similarly, for Spark, you can have a co-located environment, or it could be a standalone cluster, and we'll talk about the deployment options in just a bit. So with that, let's jump into the Kubernetes overview, and then let's look at the full stack of Spark, Alluxio with Kubernetes and how that would work. Over to you, Adit.
Thanks, Dipti. So in the rest of the talk, we'll to start talking about an overview of Kubernetes, move towards the architecture of Alluxio deployed on Kubernetes with Spark. But before we do that, let's start by defining what Kubernetes is. In simplest terms, Kubernetes is a system for deploying and managing containerized applications. What we'll cover is some fundamental concepts of Kubernetes, different options for deploying Alluxio on Kubernetes, and then we'll move on to Alluxio as a data access and orchestration layer for compute frameworks like Spark, and follow it up with a demo. So as a container orchestration platform, Kubernetes provides various features which makes it easy for applications to be deployed repeatedly in various different environments. So the first thing that Kubernetes does is that it abstracts away the physical infrastructure. So you could deploy containers regardless of what operating system or hardware the physical infrastructure is, and you could repeatedly deploy applications as containers. So the other thing that Kubernetes does is it provides services for discoveries of applications running on Kubernetes. What this does is that it makes it easy for one application to identify another application, connect to it, regardless of where on the cluster that application is running. Other features that Kubernetes provides, one of them which makes it easy to provide fault tolerance is called self-healing. So in case a container goes down, Kubernetes provides you features to relaunch that container and easily connect to that container. Other features include secret management. Secret management is a useful feature for storing sensitive credentials like credentials to connect to your Amazon S3 bucket or your GCS bucket, and also storage management to manage storage both on Kubernetes and even to connect to storage outside of Kubernetes. Some fundamental Kubernetes concepts are listed on this page here. A Docker image is a lightweight operating system and the application execution environment, which can be deployed anywhere repeatedly. Once this Docker image is running, we can call it a container. Now, in Kubernetes, the basic schedulable unit is called a pod. A pod itself might be made up of one or more containers. If you want to schedule an application containing multiple containers on the same physical host, you would combine all of those into the same pod. Kubernetes also provides you with different kinds of controllers to control the lifecycle and the number of replicas for pods. An example controller is a replica set. For example, you can specify that you always want 5 replicas of a pod on your cluster. And in case one of the pods goes down, Kubernetes would automatically find another node to launch that pod so that you always have the desired number of copies of a pod running in the cluster. Persistent volumes is a concept which is used on Kubernetes to provision storage, which may not be tied to the lifecycle of the end application. In case of Alluxio, we use persistent volumes to store the Alluxio journal, and the journal volume is persisted regardless of the lifecycle of the Alluxio application. Okay, so some more basics on how you deploy an application on Kubernetes. The first way of deploying an application on Kubernetes is using declarative specifications. These are YAMLs that you would write to specify the resources that an application should use. By resources, I mean the amount of CPU that the pod should consume, the amount of memory that the pod should consume, and what storage volumes the pod is using. Another layer on top of these declarative specs is called Helm Charts. So Helm Charts is a way of removing any redundancy that is present in the declarative specifications as well. So let's say Alluxio is running as a master worker architecture. Master is one kind of pod and worker is another kind of pod. But both of them share some configurations such as the Alluxio Docker image, which Docker image to use. So there is redundant configuration which is present when you write YAML files. And based on many people's experience, modifying these YAML files is tedious sometimes. So that's why the evolution from YAML files was to introduce something called Helm Charts, which allows you to specify all configurations without any redundancy in a single file. And this configuration is compiled into the declarative specs, which can now be deployed on top of Kubernetes. Now, another increasingly popular way of deploying applications on Kubernetes is using operators. So operators is similar to charts. Operators is an abstraction on top of the declarative specs. So operators allow you to specify a custom resource definition for an application like Alluxio or Presto, and you can specify you can build in any DevOps or domain knowledge into this operator. For example, if you want to scale down a cluster and you want to migrate state across the different workers, then this kind of domain knowledge would be built into the operator. And the way that you would use an operator is just by changing a single field in a declarative YAML, and you can pass that on to the operator, and the operator will handle the rest for you. Okay, so after covering some basics for Kubernetes, we'll talk a little bit about how Alluxio is deployed on Kubernetes using these fundamental concepts that I just described. So there are various different options for you to deploy Alluxio in Kubernetes. The deployment on the left, which is Spark with Alluxio, deploys Spark and Alluxio in two separate pods. Now, the life cycle, since it's two separate pods, the life cycle of the Spark pod is independent of the life cycle of an Alluxio pod. Alluxio runs as a long-running service on Kubernetes, and the Alluxio master and the Alluxio workers, regardless of if any Spark application is running on Kubernetes. So Spark spins up executors as and when a job arrives, accesses data from Luxio, and the executor pods are shut down as soon as the job finishes. But the data cached in Alluxio or maintained in Alluxio is persisted across different jobs and shared across jobs. So, and the deployment on the right that we have is a Presto and Alluxio in the same pod. In this case, both Presto and Alluxio are long-running services on Kubernetes. Any Spark, for example, any SQL that you run is submitted to these long-running services, which run together in the same pod. And once the query ends, both the long-running services are still present. And in this case, when you have when you're using features such as horizontal pod autoscaling, which means when you want to scale the number of nodes that this solution of Presto and Alluxio are using on the Kubernetes cluster, you would based on the load, you could say that, okay, now the load is high, I want to use more replicas for Presto and Alluxio. So in this case, both Alluxio workers and Presto workers would be scaled together since they're running in the same pod. Now, similar to what Dipti mentioned before, what Alluxio provides in a Kubernetes environment is data locality for your compute applications like Presto or Spark, even if the data being accessed is not present on the Kubernetes cluster itself. So in this diagram that we have on the right, Alluxio is used as the data access layer, fetching data from possibly both Amazon S3, GCS, or even storage deployed on Kubernetes. And the life cycle of the data across these storage systems is something that Alluxio would manage transparently for you. The other thing that Alluxio does is that is provide elasticity for your data. Like in the previous slide, we presented the solution of having Presto and Alluxio together, and we talked about scaling the number of workers up or down. Since Alluxio is natively elastic, if you scale the number of workers up, Alluxio will start caching on those workers. If you scale the workers down, and even if you lose data present in Alluxio, Alluxio always can fall back to the original source of truth, which in this case could be Amazon S3, and your data would still be available, and you would still get the data locality benefits that Alluxio provides. Okay, so we'll start diving deeper into how Alluxio is deployed on Kubernetes. In this diagram, we have a Kubernetes cluster with two hosts. The host on the left has the Alluxio master container running, and the host on the right has the Alluxio worker container running. Note that these two could possibly be on the same node. There are no restrictions. It's just for demonstration purposes. The Alluxio master uses a persistent volume. In this case, it's an EBS volume, but it can be replaced by any other kind of volume to store the Alluxio journal. And the Alluxio service, like I mentioned, the service is a concept that Kubernetes provides to make it easy for compute applications or Alluxio client applications to connect to Alluxio. In this case, Alluxio masters and workers could connect to any of the storage solutions which are listed at the bottom.
So this quick question is, you have these other containers here. I guess you're moving on to that. Can you talk a little bit about how the Spark workers or drivers are co-located with the master of Alluxio or the Alluxio worker?
Sure. So let me talk about how Spark connects to Alluxio. So in this case, like the gray slots that I have are empty slots that Kubernetes has for launching any other containers, which could be the Spark driver, it could be the Spark executor. In this case, if I specify the number of Spark executors equal to 1, what would happen is when I submit a job, a container is launched on Kubernetes to run the Spark driver. The Spark driver would then communicate with the Kubernetes master or controller and launch different Spark executors. Now, when a Spark executor is co-located on the same physical host with the Alluxio worker, it gets data locality, it gets short circuit access, and all of the performance boost that you expect from a service like Alluxio. Now, both the Spark executor and the driver pods, which are running on Kubernetes, the way that they discover Alluxio is using the Alluxio service. So the Spark driver would have a DNS host name like Alluxio master, and that would resolve to the container IP for Alluxio, the Alluxio master, regardless of which physical node on Kubernetes that master is running on. And even if the master crashes or the host crashes, which is running the Alluxio master, the Alluxio Kubernetes is responsible for launching the Alluxio master pod on a different host inside Kubernetes. And the Alluxio DNS, which the Alluxio service provides, would now resolve to the new container, and Spark would still be able to connect to Alluxio.
Great.
Okay, so we talked about some different options for deploying Alluxio on Kubernetes. The most flexible and the initial version of the initial way of deploying Alluxio on Kubernetes is using these declarative specifications. So in this screen, we can see that by using these YAML files, we have possibly 4 different YAML files that you need. I mean, these could be combined into the same file, but basically 4 different pods or configurations that you'll need to deploy on Alluxio to launch an Alluxio cluster. The one on the top is a persistent volume claim, which means that, okay, now this is the volume that Alluxio will use for storing the journal. You have a YAML for specifying any custom configuration that you want to use for Alluxio, any Alluxio site properties. And then you have 2 separate pods for the Alluxio master and worker. Like I mentioned before, there is definitely some amount of redundant configuration which is present in these YAML files. For example, if you want to size the storage that the Luxio worker should use for to store the data blocks, you would first have to change the Luxio worker YAML, specify what volume, what memory storage volume the worker should use, what size it should use, and then you would also you'll also have to specify some Luxio, modify some of the Luxio configuration in the Luxio config map. Now, an evolution of the YAMLs is, like I mentioned before, is using Helm Charts. Now we provide Helm Charts to deploy Alluxio in an easier way. So like I mentioned, if you want to change the worker storage, the amount of storage that the worker should use, you can now specify it in a single YAML file called configs.yaml, and any configuration specified in this YAML could be compiled into various different locations, and it will fill up redundant fields in the YAMLs that are presented on the previous slide. In the demo that we'll present today, we'll deploy Alluxio using a Helm chart using what we have on the screen here. So the simplest way to deploy Alluxio is you provide a minimal set of properties and the resources such as CPU and the amount of memory. You could choose to use the defaults that come in the Helm chart. So in this case, the three properties that we specify that the root of the Alluxio namespace is an S3 location, and we will use an S3 bucket as the understorage address, and we specify the credentials that Alluxio should use to access this S3 bucket. And then simply what we do is we just pass that on to Helm. We just do Helm install, pass in the configuration file, and we specify the Alluxio version to install. Note that in this command line, I have the repository as Alluxio repo, since we haven't published these Helm charts to a stable Helm chart. So we have set up an internal Helm repository, but going forward, there is no Alluxio specific repository that needs to be set up to use Alluxio with Helm.
So typically, if you have multiple containers, would you ideally have a Helm chart for each container? And is there a Helm chart for Apache Spark that you would use as well, and then have Helm chart like you've shown for Alluxio?
So it depends on the different deployment options that you have. So to deploy Alluxio, both the master and worker containers, for Alluxio as a service, you could have a single Helm chart. And for example, if you want to use Presto on Alluxio, like in the solution that we presented above, you would have either a single Helm chart for Alluxio and Presto together, or you could have an operator instead. You could have a single operator for Alluxio and Presto, and you would use that together. In Spark's case, since Alluxio and Spark are deployed separately, we could either have so Alluxio would have a standalone Helm chart in that case. Okay, so moving on to the demo portion of this presentation, give me a minute to set up. I think so. What I have is I have a 5-node Kubernetes cluster pre-deployed. Just give me a second to set up so that we can see the Kubernetes dashboard. So like I mentioned, we have a 5-node Kubernetes cluster pre-deployed. What we'll do today is we'll run Alluxio, install Alluxio using the Helm charts, and run a Spark application on top of Alluxio, accessing data using the HDFS compatible API. So let me just bump up the fonts so that everyone can see. Okay, so like I mentioned, so there's nothing running on the Kubernetes cluster as of now. The Docker images, which are used to install Alluxio and run Spark on Alluxio are pre-deployed on the cluster, so which can be pulled from Docker Hub. So you have Alluxio/Alluxio, the tag is 210 snapshot, and this is the Docker image that we'll use to deploy Alluxio on Kubernetes. So there is nothing that is present on the Kubernetes cluster. Let me just pull up my script and we can start deploying Alluxio on top of Kubernetes. So the configuration that I showed you before is what we'll use to install Alluxio on top of Kubernetes. So similar to what I showed you in the slides, so we have the properties as the mount table root UFS pointing to an S3 bucket and the credentials. So to install Alluxio, it's as simple as running, once you have the configuration file populated, it's as simple as a single Helm command. It just and I think I already showed you that before. So once I run that command, we can see that we can check the status of Alluxio on the cluster. The Alluxio master container is still pending, and the Alluxio worker containers are already running. Actually, let me, yeah, I think I did not create the journal volume, so that's why the Alluxio master container is still pending. Okay, so let me just create the journal volumes that we'll use to store the, which we'll use in the Alluxio master container. Now that we have deployed that, I'm going to try installing Alluxio using Helm once more. Before that, just give me a few seconds so that the Alluxio workers terminate successfully. So the window on the right that I'm just typing into, so I'll use that window to run the Spark submit command to submit a Spark job. Okay, so now that the Alluxio workers have shut down, I'll install Alluxio using Helm. So we can see that all containers are up. We have 4 Alluxio workers and 1 Alluxio master. To check the status of the deployment, we can exec into the Alluxio master container. The Alluxio installation is present in OPT Alluxio by default, and we can access the Alluxio CLI to check if the cluster is up properly. Since the master might still be starting up, that took a few seconds, but it looks like we can access a bucket that I specified, and these are the contents of the different files present in that bucket. So we can also use the Alluxio report CLI to see if the workers registered successfully with the Alluxio master. In this case, we see that the number of live workers is 4, which means that all 4 workers were able to successfully discover the Alluxio master using the service and register with it. So what we'll do next is we'll mount a public Alluxio bucket, which has a 2 gigabyte file, which we'll use for our demo application. So this and the demo Spark application that we'll use, what it does is that it simply counts the number of lines that are present in this file. So it'll just take a 2 gigabyte file, read the file, and count the number of lines in that file. Okay, so if you look at the file that we're going to read is called S3/sample2g. The 0% annotation that you see over there, that denotes how much percentage of that file is cached in Alluxio as of now. So 0% means that only the metadata for that file is present in Alluxio now, but the data itself is still in S3. And once we run the Spark job, we'll see this percentage go up. Okay, so to run the Spark application, we have, like I mentioned before, we have the Spark Alluxio container pre-deployed. The command that we just run, the application was, where is the application? Okay, so the application that we run was a Java program called count. We specified the amount of memory that we want to use for the drivers and executors, and we specified that we wanted to use four different instances for the executor. To check the status of the application, what I did in the window on the bottom left corner is that I simply tailed the logs for the Spark driver program, and we saw that the job, which is called count, took about 32 seconds to finish this job, and it printed out the number of lines that we have. So it just counted the number of lines, and that's what the application is. So to do just a recap of how Spark was run on top of Alluxio, so like I mentioned, to deploy Alluxio, we simply had a Helm chart. We did Helm install Alluxio, which got the Alluxio master and workers up on top of Kubernetes. And to run Spark, the only thing that we did was that we had the Spark binaries, and and access to the Spark submit CLI. We specified the Kubernetes master address, and we specified the container that we want to use to run Spark on top of Alluxio, which is what I highlighted over there, and we specified some additional configuration so that you can have short circuit access to Alluxio to get the desired performance, and we specified the path in Alluxio that you want to use with the count application. So in this case, like I mentioned before, we specified the Luxio master DNS name, which resolves to the Luxio master container IP regardless of where it's running on the cluster. And we specified the path as S3A sample 2G. So the count application ran on a sample 2G file, and it outputted the number of lines that are present. So going back to the Luxio CLI, this time if we list the S3A directory, we'll see that what we see is that the annotation denoting how much percentage of the directory is cached in Luxio has gone up from 0% to 100%, which means that the directory is completely cached in Luxio, and any subsequent accessees would access the data only from Luxio, and it will not go to the underlying storage system, which is S3A in this case. To observe the benefit, what we can do is we'll delete the pod which is running the Spark driver, and if we run the Spark application again, we'll see some amount of performance improvements. Okay, so with that, that's the end of the demo, and I believe we are open to any questions. So, like I mentioned before, previously we saw that this application took about 30 seconds, and now it's taking about 7 seconds to run, which gave us some amount of performance improvement based on your application.
You want to jump back to the slides and
Yes.
summarize? And then it would be a good time to think about your questions. We'll open it up for questions in just a bit.
Okay, so today, what did we talk about? So we talked about Alluxio as a data orchestration platform. We described different use cases for Alluxio and how that fits to Kubernetes. And Alluxio works really well in Kubernetes. It provides an elastic it provides elasticity for your data, similar to the way that Kubernetes provides elasticity for your compute. And take my word on this, that's my unbiased opinion as an Alluxio employee. We showed you how to run Alluxio in Kubernetes. We described different deployment options that you might want to use. We described the deployment option with Alluxio long running alongside Spark, and we also described Alluxio and Presto running together. In the demo that we presented, we ran a Spark application on Alluxio, accessing data from Amazon S3. The first run fetched the data from Amazon S3, cached it in Alluxio, and any subsequent accesses were much faster, and we observed some amount of performance gains. Cool. So I think that's all we had prepared for you guys. Like Dipti mentioned, we are happy to receive any questions at this point.
Great. Thank you all so much. We do have a few questions that have come in. The first question that we have is, what is the difference between Presto Alluxio versus Starburst Presto in terms of performance?
Yeah, that's a great question. So Presto is an interactive query language which allows you to access data from many different places. And Alluxio can be used as a caching layer as well as an orchestrator for Presto. Presto has a couple of different flavors. So Presto SQL is the open source version of it, and Starburst Presto is based on Presto SQL and is the optimized version of it. So Starburst Presto, for example, comes with a cost-based optimizer that's built in that could be higher performance. So when you look at the two together, Alluxio kind of presents the same advantages for both Presto and Starburst Presto. But because Starburst Presto is an optimized version, depending on the queries and the SLAs you have, you might want to pick Starburst because of its cost-based optimizer. So hopefully that answers the question.
Perfect. Thank you. The next question that we have is, can I access data directly from S3 within K8s? Or if yes, how does Alluxio help?
Yeah, Adit, actually you just showed the demo with S3. So is there a way to access it directly from Kubernetes without Alluxio?
So to access S3 directly from Kubernetes, you would use an HDFS client, which would essentially, you could still use it, but there would not be the benefits that we talked about with regards to data locality, or the translation of the API translation is more on the client side and not on the Alluxio server side. Just by having the API translation on the server, that's more efficient.
So would it use the HDFS S3 adapter? Would that be the only kind of way of accessing S3?
Correct. So you could potentially use the HDFS S3 connector to access S3 directly from Spark.
And that's one more layer of indirection. So the performance would, if you would run that, it would take more than 32 seconds, perhaps, if it's going through the S3.
Correct. So even the first access, since the metadata is typically slower when you use a connector like S3, the HDFS connector for S3, and Alluxio already caches the metadata, the performance could be even a little slower for compared to 32 seconds, even for subsequent accesses, and with that would remain a constant.
Great. The next question that we have is, I hear that Kubernetes helps with hybrid cloud environments. How would this work, and does it handle the entire stack?
So Kubernetes can be expanded across environments, theoretically, across an on-premises environment and a public cloud environment, let's say. how would that work? Is it a single cluster that you extend across? And would where do you create the pods that are the same across both environments?
Yeah, so that's an interesting question. So we have several interesting use cases for Kubernetes in which one of the use cases is in which you have a Kubernetes cluster on premise and you burst into the cloud as and when your load increases. So in a case like this, what there are other projects in Kubernetes which are called federation or which also provide federation. What federation does is that you could have a small cluster pre-deployed on the cloud and you can have a bigger cluster on premise. And once the load on the on-premise cluster grows, it simply uses the smaller cluster and can even grow that smaller cluster, which is already present in the cloud, out to run your compute applications. So the solution with Alluxio is let's talk about the Presto Alluxio case, and I already talked about horizontal pod autoscaling previously. In a cloud bursting case like this, what would happen is that Alluxio Presto, let's say, start off deployed only on the on-premise cluster, and the load increases, and let's say you have more replicas that you need in the cloud. Alluxio Presto would simply be deployed on the cloud nodes for a use case like this, regardless of so you could specify that Alluxio Presto be deployed on all the nodes in the cluster, and as soon as the cluster size grows, the size of the Alluxio Presto could also grow elastically.
So Kubernetes will basically handle the compute part of it, but if your data is only in the on-premises environment, then you need something like Alluxio to essentially make that available to the compute on the pods for Kubernetes in the public cloud.
Correct. So in this cloud bursting use case that we just talked about, let's say the cloud cluster grew, Alluxio is deployed on the cloud cluster, and it would cache the data on the cloud cluster for locality. And this also reduces the amount of traffic that you have from your cloud deployments onto your on-premise environment, which kind of leads to different cost savings and other benefits.
Great. Thanks. Any more questions?
Yes, we do have a few more questions. The next question that we have is, how do you make sure two different pods are running on the same host?
Could you repeat that question, please?
Yes, the question is, how do you make sure two different pods are running on the same host?
So two different pods you can ensure that two different pods are running on the same host by using labels. In the case that I described before, if you want Alluxio like Presto workers and Alluxio workers to be run on the same host, if you want to guarantee that, the way that you would do that is by combining these containers in the same pod. So the schedulable unit in Kubernetes would be the pod, which could have multiple different containers, possibly belonging to different frameworks. In the left side picture, the way that you could ensure that the Alluxio pod and the Spark Executor pods launch on the same node is by using labels. So you could specify a selector for the Alluxio pod, specifying that only run on some nodes, let's say, are labeled Spark Alluxio, and specify a similar label for Spark Executor so that even Spark Executors are launched on the same set of nodes.
Great. The next question that we have is, Presto and Spark might need Hadoop as well. Where do the Hadoop components live within the K8 cluster?
So, for example, one of the things, the Hadoop components that Presto requires is the Hive metastore. And in this case, the container that you use to deploy Spark would have these services in it. So you could control which services to launch on Kubernetes by specifying a different option to the entry point for this container. But any Hadoop services that the Presto Luxio stack depends on, such as the Hive metastore, would be present in the same container itself. So the same Docker image would have the execution environment for Presto, for Alluxio, and any other Hadoop component such as the Hive metastore.
Great. We do have one last question. That question is, does Apache Spark have a K8 operator? How would Alluxio work with that?
So the short answer is that Apache Spark does have a Kubernetes operator. The details on how Alluxio would work with that operator are still to be finalized, but it should work, theoretically, it should work similar to what we just described.
If you have Spark pods that get created, then you could just basically co-locate the Alluxio pods with those to achieve data locality, perhaps. Great. All right. Any other questions or time to wrap?
That was the last question. Is there anything you guys would like to add before I close things out?
No, thank you very much for your time today. Appreciate it, and I hope you learned how Spark works, how Alluxio works with Spark to accelerate your Spark workloads in your Kubernetes environments. Thanks, Adit. Thanks, everyone.
Great. And with that, I'd like to thank Adit and Dipti for a great presentation today. I would also like to thank Alluxio for sponsoring today's webinar. And lastly, thank you to everyone who attended today. We hope you learned something new that will help you in your developer career. Have a great day, and we'll see you next time.